Hello students, welcome to All Force e-learning channel. This is K. Nageshwar Rao, your physics faculty. Today I am dealing with session number 32. Till session number 31, few concepts, starting from session number 28 to session number 31, fundamentals and few important concepts connected with the motion in a straight line chapter were already introduced to you. Let me recollect what has been completed so far in those 4 sessions. See, in motion in a straight line chapter, we start with very fundamental data like distance, displacement, okay, their definitions, and followed by that, if they change with the time, several, like velocity, speed, types of velocities, types of speed, like that. One important fundamental key point that you should know about distance and displacement is this one. Distance is always greater than or equal to displacement, modulus of displacement, isn't it? Distance can never be less than displacement. This is a very important key point connected with that. And if a body is revolving in circular path, or if a body is traveling along a straight line path, or if a body is traveling along a curved path, you have already seen in the previous sessions how to find out the distance covered by the body, how to find the displacement of the body. If at all, if the body is traveling along the straight line, no worries, whatever distance it covers, that is same as that of displacement. But one difference is distance is a scalar quantity and displacement is a vector quantity. What if a body which is traveling along straight line, if it takes turn, if it turns back and if it travels again, then distance and displacement both will be different. Okay, so these are 2 points that you should remember. And next, if a body is revolving, if it is moving in circular path, for example, imagine a circular path something like this. A circular path something like this. Now in this path, what do you see? A body is traveling from A to B. It has traveled from A to B. If you wanted to find out a distance and a displacement of the body, the data given in the picture can be used. How much angle the arc is subtending at the center? It is subtending an angle equal to theta, isn't it? And the displacement, as you see in the diagram, what is the displacement? 2x is the displacement. And what is the distance? The arc length from A to B, whatever arc length is there, which is subtending an angle theta, that arc length is distance. And what is that distance and displacement? Distance is this one. D is equal to r theta, where r is the radius of the circular path, and the displacement 2x is equal to 2r sine theta by 2. 2r sine of theta by 2. So these are some key points connected with the distance and displacement, you should remember. And followed by that, if distance changes with the time, you call it as speed. If velocity changes with the time, you call it as, if displacement changes with the time, you call it as velocity, isn't it? And speed, again, it can be categorized into a few more types like average speed, instantaneous speed, uniform speed, non-uniform speed. Similarly, velocity too can be categorized into 4 types. Average velocity, instantaneous velocity, uniform velocity, and non-uniform velocity. So you are already informed about all the definitions, but we have dealt much with the average quantities of speed and velocities. If you look at average speed expression, what is average speed expression? Total distance, this is the equation for average speed. What is that? Total distance divided by total time taken, isn't it? Or delta r by delta t, that's how you will write. See, when it comes to the average velocity part, this is the equation. What is the equation? V average is equal to displacement divided by time taken, or it can be expressed as delta r bar by delta t. Clearly, the vector and scalar natures were distinguished in both the equations. Remember children, whatever situation you are dealing, it doesn't matter. Whatever description he has given about a particular body's motion, all that you need to do is, if you wanted to find out average speed, you have to identify what is the total distance covered by the body and you have to replace it in the numerator. And what is the total time taken by the body to cover the distance, you have to identify and you have to replace it in the denominator. In this equation, you will get average speed. Similarly, average velocity also. Whatever data is, let us say the entire data in the question is given in terms of velocity and displacement. Time is not there. Okay. Or entire data is given in terms of speed and distance. Time is not given. Can't you find time from distance and speed data? Of course, we can find. So like that, you have to extract the information, you have to use these equations and you can calculate average velocity as well as average speed. Remember children, one important difference between these two things is, one important note that you should remember. If a body is traveling along straight line path, In that case, average speed, magnitude and average speed and magnitude of average velocity both are same. Both are same. Okay. What if, if a body is traveling, let us say it is traveling along x direction for some time with some velocity or with some speed, and then it has taken turn towards y axis and it has traveled for some time with some velocity. In that case, you are supposed to consider the vectorial approach to find out average velocity. These are few points that you should remember. And the last one is instantaneous velocity. This is the expression for instantaneous velocity. What is that? Instantaneous velocity, it is expressed as limit delta t tending to 0, delta r bar by delta t is equal to dr bar by dt. Instantaneous velocity in the sense velocity at a particular instant. Velocity at a particular instant. Let us say if you are traveling on a bike, whatever speedometer reading that we see, that gives us in fact what reading? Instantaneous velocity reading, isn't it? When we travel on the bike, when we ride a car, what happens? Okay, continuously we keep on accelerating the car and we decrease the velocity, we increase the velocity. So the speedometer's needle, it doesn't point at a particular number, it fluctuates. So whenever you look at the speedometer screen, whatever number it is pointing at, the needle, okay, so that particular number indicates the instantaneous speed of the car. Okay, so these are key points, children. So now let us continue with further discussion. Students, let us continue with the further discussion. We have started with the fundamentals like distance, displacement, right? If distance changes with the time, we call it as speed. Speed is categorized into 4 types. And if displacement changes with the time, we call it as velocity, and velocity is categorized into 4 types. And what if velocity also changes with the time? We call it as acceleration. To deal with the acceleration data, we need to have knowledge of graphs. I'll tell you what graphs, what kind of graphs we'll be dealing with. See, graphs are very, very important. I want you to give a special attention towards this discussion, because graphs are having physical significance in various problems. Okay, in further topics also we'll be using these physical significances. Graph, when you draw a graph, it speaks some information to us. It tries to convey something to us. We have to identify what it is trying to convey. We have to decode the data. Graph is what? Basically it is drawn between 2 physical quantities. How one physical quantity is changing with respect to the other physical quantity, right? So definitely some information, we can extract from the graph. Okay, I'll start with the position time graph, and I'll discuss velocity time plot, and I will discuss physical significances of both the graphs, and later we'll proceed with the discussion connected with acceleration. Okay, let us see. Graphs. I'll start with the position time graph, or simply you can call it as ST graph. I will describe various situations. Corresponding to those situations, how the graph appears. Let us try to identify that first. First I will start with this one. Let a body is at rest position. Body at rest. Let us say this is x-axis, this is y-axis. On the x-axis I will take time t, which is measured in seconds. This is the origin. On y-axis I will take position. Let us say it is represented with s. It's measured in meters. I'll assume like that. At a particular instant of time, or at 0 seconds. See, 0 seconds in the sense of the time when I started monitoring the situation. From that time onwards, I'll take it as 0, and from that time onwards I will count the time as 1 second, 2 seconds, 3 seconds, like that. Okay. So a body is at some position. It has some coordinate. Let us say this is the coordinate, and the clock is ticking. The time is running. At 1 second also the body is at rest position, no, so it's not moving. So its coordinate remains constant even at time equal to 1 second. Even at a time is equal to 2 seconds, it remains same. At a time equal to 3 seconds, it remains same. Like that, continuously it coordinate, its position coordinate, it remains constant. Its position doesn't change. Okay, that's what we call it as rest position, right? If position is not changing with the time, then the body is said to be at rest position. So if you join all these coordinates, what you will get? If you join all these points, what you will get? You will get a straight line. So remember, children, the position time plot of a body which is at rest position is a straight line parallel to not x-axis, parallel to time axis. Of course, here in the graph it is parallel to x-axis only. What if I consider displacement here on the x-axis, time on the y-axis? The graph will be a vertical straight line, vertically straight line. So remember children, this is how you have to recollect the data connected with body at rest position. The graph will be a straight line, position time graph will be a straight line parallel to time axis. Okay, and let me describe one more situation. Let a body is undergoing uniform motion. Uniform motion in the sense it's moving with a constant velocity. It's moving with a constant velocity. It means it is covering equal displacements in equal intervals of time. Such a kind of motion is called as uniform motion. We all know that. So let us try to draw the graph that can describe this situation, uniform motion. On the x-axis I will take as usual time, which is measured in seconds, and on y-axis I will take position. Let us say it is measured in meters. Okay. So the graph will be something like this, passing through the origin. It is because, let us say in 1 second, the body has undergone a displacement equal to 1 meter. In the next second, it has undergone a displacement equal to 1 meter. In the next second, like that, in equal intervals of time, let us say it has undergone equal displacements. So what will be the coordinates in the position time plot? 1, 1, 2, 2, 3, 3, 4, 4, and so on, isn't it? So when you join those points, what you will get? You will get a straight line. You will get a straight line passing through the origin. Okay, so this is how the graph appears, and this thing has got a physical significance. Before I describe or I explain the physical significance of this graph, I would like to recollect one important point. All of you might be knowing about slope. For example, slope in the sense what, if you are having a straight line like this, let us say that straight line is making an angle theta with the horizontal. Okay, so mathematically slope is expressed as tan theta. Slope is expressed as tan theta. For example, I know these are adjacent side and opposite sides. Let us say this is x, this is y. Okay, then this tan theta can be expressed as y by x, isn't it? I want all of you to remember this data. Slope is expressed as tan of angle made by the line with the horizontal, or the same thing can be expressed as, if it is in xy coordinate system. If this line is an xy coordinate system, y coordinate or y coordinate divided by x coordinate gives us what? Slope. Now look at this graph. I'll assume that this particular point corresponds to some value s0. Okay, corresponding to this point there will be time coordinate also, right? I'll take it as t0. I'll take it as t0. Let us say this line is making an angle theta. This line is making an angle theta. And what kind of motion is this? Uniform motion. The body is moving with constant velocity. In this case, if you write expression for slope, what you will get? Slope is equal to tan theta, which is equal to, look at this picture. From here to here, what is the length? S0, right? So if this is S0, this is also S0, isn't it? And from here to here, how much is the distance of separation? T0. Okay, so opposite side by adjacent side gives us what? Tan theta. So here this tan theta can be written as S0 by T0. Okay, let us look at this equation in a general view. What you have taken in the numerator, you have taken displacement. In the denominator, what you have taken? Time. Displacement divided by time, what it gives? It gives us velocity. So what is the physical significance of position time plot in case of uniform motion? The slope. Even in case of here also you can talk about the same physical significance. Okay, in case of position time plot, the physical significance of slope is it gives us velocity. Therefore slope gives velocity. Slope gives velocity. Even here also the slope gives velocity. Sir, the body is at rest position, so it doesn't possess any velocity. Of course it doesn't possess any velocity. How much is the velocity if the body is at rest position? 0. So what is the slope of this horizontal line? 0, isn't it? So slope here it is 0, it means velocity is 0. Velocity is 0 in the sense body is at rest position, or speed is 0, it means body is at rest position. And here slope has some value, it means whatever. Let us say in this particular case I have given the coordinates also 1, 1, 2, 2, 3, 3. If that is the case, this theta will be 45 degrees. So tan 45 will be how much? It will be equal to 1. So slope is equal to 1, isn't it? And slope is 1 in the sense the velocity is what? 1 meter per second. 1 meter per second. So this is the some useful information connected with the position time plot. Let me continue with another type of graph, like position time plot only. I'll describe the situation. Here the body is considered to be at rest position, and here body is undergoing uniform motion. Now I'll talk about a body which is undergoing non-uniform motion, Okay, let me pick up this third possibility. Non-uniform motion. If body is undergoing non-uniform motion, how this graph appears? As usual, on the x-axis I will take time, which is measured in seconds. On y-axis I will take a position, which is measured in meters. Let us say the graph is something like this. Okay, something like this. It's non-uniform motion. If it is a straight line, it represents what? Uniform motion. But here it is a curve, something like this. So what it represents? It represents non-uniform. Non-uniform motion in the sense it is covering equal displacements in unequal intervals of time, or unequal displacements in equal intervals of time. If that is the situation you see with a body in motion, then you can say that the body is undergoing non-uniform motion. So in this case also there are physical significances. Even here, I'll consider two time intervals. Let us say corresponding to this point time is t1. I'll consider one more point here corresponding to this coordinate. Let time is x coordinate is t2. Okay, since this is a point in two-dimensional coordinate system, it will have y coordinate as well, right? So corresponding to this point, I'll take y coordinate as s1, and corresponding to this point I will take y coordinate as s2. Now I am going to draw a line joining these 2 points, something like this. Let us say the line is AB. AB is the line which is joining these 2 points. Okay. Now I will make some extra construction here, like this, additional construction. Let us say this point is C. Now look at this graph. This is equal to how much? S2 minus S1. This is S2, this is S1, so this is equal to S2 minus S1. If this is S2 minus S1, this BC will also be S2 minus S1. If this is T1 and if this is T2, this particular length will be what? T2 minus T1. So this can be, this AC is nothing but T2 minus T1. Now let us say this line AB is making an angle theta with the horizontal. Okay, I am trying to find out the slope. So let us calculate what slope is in this case. Therefore, slope of AB line is equal to, AB is what? AB is the point line connecting the 2 points whose coordinates are S1 T1 and S2 T2. And what is its slope? Opposite side, BC by AC. Why did I take like this? Slope of AB is tan theta, like the way we have written here. Tan theta is what? Opposite side by adjacent side. So BC by AC, and this BC can be replaced with what? S2 minus S1. AC can be replaced with T2 minus T1. Or this can also be written as total displacement divided by time taken. Okay, divided by time taken. This is how you can write. Now look at this picture. What do we call this as? Total displacement by total time taken. This is called as what? Average velocity's magnitude. This is called as average velocity's magnitude. It means in case of a non-uniform motion, if you measure the slope of a line joining 2 points, it gives us average velocity corresponding to that particular time interval. Here the time interval is T2 minus T1. So slope is equal to, in this case, what? Average velocity. Average velocity. See, if the curve, a curve is seen in position time plot, that doesn't mean the body is traveling along curved path. The body, I'll assume that the body is traveling along straight line. Is such kind of curve is not possible? It's possible. When this kind of curve is possible, if the body is covering unequal displacements in equal intervals of time or equal displacements in unequal intervals of time. In such cases, such kind of graph is possible. So remember children, slope of line in non-uniform motion position time plot gives us what? Average velocity. If you wanted to find out instantaneous velocity, what you can do is, let us say I wanted to find out instantaneous velocity corresponding to this point. Draw one tangent corresponding to this point like this. Okay, this tangent is drawn at point B and find out this slope. Since all these details are available on the graph sheet, whatever line you draw, for that line you can find out the slope, because you will define the scale. So entire data will be there on the graph sheet. So wherever you draw any line in the graph sheet, for that line you can calculate the slope. So whatever slope you calculate corresponding to this line which is drawn at point B, the tangent at point B, that slope gives us information about instantaneous velocity. So these are the physical significances that you should remember. Okay children? So body at rest position, it's a straight line parallel to time axis. Uniform motion, it's a straight line passing through the origin. And non-uniform motion, it's a curved path. And here physical significance is what? Slope of position time graph of uniform motion gives us the velocity. Here if velocity is constant, then whatever value of velocity is there, that is nothing but average velocity, that is nothing but instantaneous velocity also. Okay, in case of velocity, uniform velocity, all velocity or average velocity or instantaneous velocity, all will have same value. Because at any point if you draw the tangent, it overlaps with the straight line, and whatever slope you will calculate, it will be same as that of slope of line that is taken between 2 points. Okay, so these are the points that you should remember children. Okay. Now let us discuss about velocity time graph. What is velocity time graph? Here I'll go with limited data. Okay, after the completion of acceleration part, I will get back to velocity time graph again, and I'll discuss few more other details connected with velocity time graph. Okay, so one significance is there, one physical significance. Okay, we need to know that physical significance before we proceed further. So I'll describe the situation. I'll let the body is moving uniformly. You can call it as VT graph. As usual, I'll consider time on the x-axis. Let us say it's measured in seconds. This is origin. So velocity is taken on the y-axis. Okay, it's measured in meters per second. Okay. Now, what is the situation? The body is moving uniformly. Uniformly in the sense what? Its velocity is constant. If velocity is not changing with the time, what does it mean? Let us say if the body is at rest position, what is its velocity? It's 0. So whatever graph you draw, that graph, it overlaps with x-axis like this. It overlaps with x-axis or with time axis, isn't it? Let us say if there is an object which is moving with a constant velocity, some 5 meters per second or so. Okay. Or I'll take like this, v naught. A body is having velocity equal to v naught, and it is not changing with the time. As the time is ticking, its velocity is still v naught only. At time equal to 1 second, v naught only. At a time equal to 2 seconds, V naught only. At a time equal to 3 seconds, V naught only. Like that, continuously it is maintaining the same constant velocity. If that is the situation, okay, when you join these 2 points, when you join all these points, what you will get? You will get a straight line. Again here, whatever straight line you have drawn, that straight line is parallel to which axis? Time axis. It is parallel to time axis. So remember, for a body which is moving with the uniform velocity or which is in uniform motion, the velocity time graph is a straight line parallel to time axis. Okay, and let us think about any physical significance connected with this one. Corresponding to last point, I will consider the time as let us say t naught. Okay, let us say we are interested in calculating the area under this graph. This is what area enclosed by this graph, isn't it? So let us find out what that area is. Area under the graph is equal to, this is like what a rectangle, right? So from here to here, what is the value t naught? From origin to this point, what is the value? V naught. So what will be the area? V naught into t naught. Look at this expression in a general view. It is a product of velocity and time. When you take a product between velocity and time, when you multiply time and velocity, what you will get? You will get displacement. You will get displacement because velocity is equal to displacement by time. So displacement is equal to velocity into time. Velocity into time. So this V naught into T naught is nothing but the displacement. Is nothing but displacement. So with this, we can draw one conclusion. When you calculate area under velocity time graph, what information you can access? You can access information corresponding to displacement of the body. So the physical significance here in case of velocity time graph is area under the graph will give us information about displacement, and this point will be used further in few derivations connected with the acceleration. So you need to remember this point. What area under velocity time graph gives us information about displacement. Okay. Okay. So with this, we'll proceed further. Okay. Let me start discussing about acceleration now. Okay. There are a few other graphs like average velocity, average speed. Here, instantaneous velocity. Here also we can talk about average acceleration, instantaneous acceleration. Okay. So first, let us see what acceleration is. How into how many types it was categorized, and then we'll get back to velocity time plot again. Okay. So this physical significance you need to remember. Now acceleration. This is what I have been talking about. Acceleration. What is acceleration? Acceleration in the sense time, rate of change of velocity, isn't it? Very simply, you can say like that, rate of change of velocity. If velocity is changing with the time in the sense of two things comes into picture. Change, what kind of change? Is it increasing or decreasing? If it is increasing, we call it as acceleration. If it is decreasing, we call it as retardation. In fact, there are different names, or in different ways you can call the situations. Like if velocity is increasing with the time, you can call it as acceleration or positive acceleration simply. If velocity is decreasing with the time, you can call the situation as retardation or deceleration or negative acceleration. Okay. So so if velocity is changing with the time, okay, what do we call it as? We call it as acceleration. So let me write this fundamental data. What is this physical quantity? Acceleration. In fact, most of the theory connected with one-dimensional motion is dependent on this acceleration parameter. We'll be dealing with the kinematic equations and their applications. Everywhere we see this acceleration term. Okay, so let us find out. Acceleration is a vector quantity. It's a vector quantity. Okay, rate of change of velocity is nothing but acceleration. That's how you can define. And coming to its mathematical equation, you can write like this simply: what velocity divided by time. Velocity divided by time. Coming to its units, meter per second square in SI system. In CGS system, you can write units as centimeter per second square. Okay, and what kind of quantity is this? Is it a vector quantity or scalar quantity? It's a vector quantity because it's connected with velocity. It's a vector quantity. This is another key point connected with this one. It is a vector quantity. Vector quantity. And you can write the dimensional formula also. All of you are aware of dimensional formula, how to write a dimensional formula for a given physical quantity. And its dimensional formula is what? M power 0, L power 1, T power minus 2. That's how you can write. Okay, so this is some fundamental data connected with the acceleration. Again, like the way velocity was categorized into 4 times, acceleration too can be categorized. Okay, let us see. A bar, the average acceleration, instantaneous acceleration, and what else? Uniform acceleration. This is very important. Obviously, the fourth possibility is non-uniform acceleration. Non-uniform acceleration. So, what is average acceleration? Average acceleration is similar to what average velocity. Here we talk about change in velocity, right? So, total change in velocity divided by what the total time taken for that change can be called as average acceleration. And instantaneous acceleration is acceleration at a particular instant. Okay, and uniform acceleration in the sense constant acceleration. Acceleration is what? Change in velocity with respect to time. If velocity is changing equally in equal intervals of time, corresponding acceleration is called as uniform acceleration. If it is changing non-uniformly in the sense there is a change in equal in velocity changes in in unequal intervals of time, or unequal changes in velocity in equal intervals of time. If that is the situation, you call the acceleration as non-uniform acceleration, and this is what we'll be dealing with, uniform acceleration. Of course, we can write equations for all these things. Average acceleration, it can be expressed as a bar is equal to delta v bar by delta t, change in velocity by time taken. And instantaneous velocity, it can be written, sorry, instantaneous acceleration, it can be written as dv bar by dt, like that. You know, you can write mathematical equations for average acceleration and instantaneous acceleration. Okay, so further in the next coming classes we will proceed with uniform acceleration. Whatever physical significance of velocity time graph here we have identified. What is that? Area under velocity time graph gives us what data? Displacement. So using this point, using this physical significance, we will try to develop a theory connected with a motion, okay, connected with uniform accelerated motion. Okay, children, that's what we will be continuing in the next session. Thank you.